Thank you, Philip. Thank you to the organizers for giving me this opportunity to present this work. So this work was done in collaboration with a few colleagues of mine. We come from different backgrounds. So, Ali comes from a background of, let's say, gravity. Adam, everyone, we know Adam. And then my colleagues from Italy actually belong to the quantum information group, Cosmo Lupo and Stefano Mancini. So, and this is actually the group where I'm working now on the quantum error correcting codes. However, I still kept my interest because my background is in Mach-centric methods and application of inference methods in physics. So today I would like to share, let's say, a few of my doubts on some topics concerning the geometrization of a Jaynes MaxEnt method in inference. So my general motivation, let's say, is that one of applying geometric methods in physics, for example, applying Riemannian geometric methods to quantum computing, or applying inference methods in physics, for example, I think about statistical mechanics. And if I have to be more, let's say, drastic in my choice, I would say that I would like to follow the idea of reducing the laws of physics to geometry. So I think about Einstein's theory of gravity. And this one actually it's even more, let's say, radical, reducing the laws of physics to inference. And I think about mostly the work of my advisor, Ariel Katiccio. So of course, usually I apply geometry to physics, apply inference to physics. Now I just would like to find out possible connections between geometry and inference, geometry and probability calculus, geometry and statistics in general. Of course, I'm not the first one to have this problem in mind. So to be more specific, one of the motivations that actually, some of the questions I will try to answer, if possible, is whether or not geometry elements are useful in probability calculus and statistics, whether or not geometric concepts may be useful for understanding Jaynes MaxEnt method. And unfortunately, the last question, I will not be able to answer this question, provided that actually it's meaningful, because I still know the problem is still not well formulated. So this question is so I'm wondering whether or not it's possible to combine geometric methods and inference methods to describe the dynamics of the quantum systems in the presence of a partial knowledge. Okay, this problem may not be formulated. I will not give an answer to this question, but it gives me some reason to keep on going on this project, especially recalling some words by Wheeler, who actually said that it's appealing and stimulating to consider quantum mechanics that's rooted in making statistical inferences based on observed experimental data. Of course, I think about dynamics and geometry when I think about Wheeler. I think about this connection between inference and quantum theory. So my general idea is that one of connecting geometry, inference, and quantum theory, let's say in a bigger picture. Of course, this would be ideal. So discussion points of this talk are going to be, first, I just mentioned the concept of statistical distinguishability between quantum states probability distributions. Then I will go over some elements of differential geometry for describing classical probability distributions. And I try to provide a geometric picture of Jaynes MaxEnt, slightly modified as Jaynes MaxEnt. Then I do the same for the quantum framework. And at the end, I end with many questions and few remarks. Okay, the first thing I would like to point out is this concept of statistical distinguishability. Actually, I just came aware of this work not long time ago, and actually, I must confess I still have to fully appreciate the result of this work. So basically, the first connection between one of the main connections between statistics and geometry, were the one provided by Wouters in 1981. We actually showed, maybe an expected result, that the statistical distance between two preparations of the same quantum state, so a statistical distance between the preparation of two quantum two perturbations of the same quantum state, actually it's equal. So this here I see statistics, here I see geometry. It's equal to the angle between two rays, C1 and C2, in a Hilbert space. So two apparently different concepts actually may be shown to be presented in the same way. So this result goes back to 1981. Of course, the concept of distinguishability provided by Wouters was dealing with geometry of pure states. But actually, the concept of distinguishability may be applied even to probability distributions as well, in any probability space. In particular, if you consider the space of probability distributions, the line element, let's say, distinguishing two neighboring probability distributions, assumes this form. The same, actually, now in 1985, Campbell actually shows that this kind of line element quantifying the infinitesimal distance between two neighboring probability distributions actually is also the natural metric associated with correlations between random variables. So the idea that he presented was the one to introduce geometry into probability calculus in the following manner. So you choose a probability distribution and then defines the inner product between two random variables as the expectation value of the product of the random variables. Then differential geometry enters when you consider variations of the probability distribution, or if you assume the probability distribution depends on some parameters, you consider the variations of the parameters themselves. So this is just a slide to show a little bit the formalism. So we're talking about a probability simplex that actually yesterday evening was brought on during the panel discussion. So we consider a space of probabilities belonging to an n-dimensional space. Each one of them can be decomposed into a basis for this space, and they satisfy certain constraints, namely that the sum of the probabilities, the components, let's say, of the probability vector satisfy this relation, normalization condition, and each one of the components is bigger than is positive, let's say. Then the idea is that, okay, I'm referring to the work here by Brownstein and Caves, actually. So this is really following their work. So the idea is that we like to consider probability paths on this probability simplex. And so in order to do this, we introduce, let's say, the notion of tangent vectors. Those vectors are simply those ones that satisfy this special constraint that actually is a consequence of the normalization constraint. And then we like to, at the end, let's say, define the action of a tensor metric on the either vectors or these objects named, namely one forms. So let me consider the dual vector space to the space of vectors. It's made up of one forms. And the special property of these quantities is that the one form, let's say, sends a vector to a scalar. It's that the action of this one form over a probability space is actually equal to an expectation value of the random variable itself. So the random variable actually, in the statistical language, it's equivalent to the one form in the geometric language. So once we have introduced vectors, one forms, and all these quantities, we consider, let's say, the action of a metric tensor over the random variables. And actually this one, so this is a geometry, let's say I see this like geometry. So the action of the metric tensor over random variables, it's equal to the, so here I see the statistics. So it's expectation value or the product of the random variables themselves. And these quantities, this R and P, R and L, sorry, are simply quantities that allow you to go from, let's say, a vector, the space of vectors to the space of one forms. And the names actually lowering and raising are simply related to the fact that the lowering operator sends a vector to a one form. The vector has, let's say, components with an upper index. When you apply this operator, it sends you to one form that has a lower index. And here vice versa, basically. So within this framework, it's possible to show that the statistical distance, the geometric distance between, so let's say the infinitesimal line element on this probability space, it's simply given by this expression that actually it's equal to the distinguishability metric provided by Wouters. As a side remark, the metric on the probability simplex, it's given by, let's say, the tensor components are given by this expression. This is due to Fisher in 1922. And actually, if we see these probability distributions belong to this simplex as parameterized in terms of parameters theta belonging to a m-dimensional vector space, actually it's possible to define the notion of distance on the manifold with this kind of element. So it's like a submanifold of the entire manifold. And actually the line element, so the metric tensor components actually can be expressed in terms of the known Fisher-Rao information metric that we were discussing before. So let's say this is the geometrical, let's say, framework within which I'm trying to move. And then one of the questions that I was posing is if it's possible to use this formalism to provide a geometric viewpoint of Jaynes MaxEnt. It's not really Jaynes MaxEnt, but let me go further ahead. So I'm always referring to the work by Campbell in 1985, when he uses the concept of minimization of the Kullback information that provides, let's say, a measure of comparison between two distributions. I'm simply, let's say, considering replacing the minimization of the Kullback information, this is from a mathematical point of view, with the maximization of the logarithm of the relative entropy. So Jaynes MaxEnt, we said, assigns probability distributions. However, let me assume that instead of considering, let's say, the ordinary Shannon entropy, I consider the logarithmic relative entropy subject to these constraints. So the maximization of this entropy, whenever let's say, the prior is uniform, is equivalent to maximization of the Shannon entropy. And the solution to this maximization problem is given by this probability, this MaxEnt estimate, let's say. From a geometric point of view, this quantity is actually may be seen as the solution of a differential equation, a nonlinear differential equation, that actually describes the flow lines, so this pk lambda, the flow lines of a vector field that actually belongs to a subspace of a tangent space to the probability simplex. So I can see, for example, for lambda equal to 0 to lambda equal lambda final. Lambda final is the one that actually satisfies this constraint. It leads me to the final MaxEnt estimate. So I see like a transport from a prior position to a final position through the solution of this equation, let's say. Actually, this one is just because at the beginning I wanted to see, let's say, like the MaxEnt estimate, but actually this formulation holds for any. So I do not have to assume uniform priors for this one. So the conclusion to this first point is that the generalized MaxEnt estimate of a probability distribution given a prior and information constraints is found by following an integral curve through the prior, which is orthogonal in the Fisher metric, to the higher plane defined by the information constraint until the constraint is satisfied. So this was like for the classical part. So it's assigning probability distributions, seeing them as a kind of a motion, let's say, transport from a prior to a posterior, assuming that instead of maximizing the Shannon entropy, I maximize the relative entropy, subject to the fact that I'm limiting my, let's say, initial prior knowledge to a uniform knowledge. So the idea is it possible to do probably the same one for the quantum framework? In the quantum framework, so I'm always following this work by Brownson and Caves. We replace the probability distribution, so the probability simplex, by a space of the manifold of density operators belonging to a certain space of all linear operators of an n-dimensional Hilbert space. It actually can be decomposed in this way with certain properties, hermeticity, a trace of the density operator, it's 1, and actually it has positive eigenvalues. An arbitrary vector in this manifold of density operators can be written in this way, where this quantity is simply the matrix elements of this operator, vector operator. And again, so we just do the same. We introduce the tangent vector in ρ with this additional condition that is a consequence of the normalization condition. And then again, we introduce the one forms in this manner. So in analogy to what we said before, that random variables are going to be where, let's say, statistical random variables were one forms. Here, one form is replaced by quantum observables. And the action of these one forms over the vectors, it's given by the expectation value of the quantum observable. In analogy to what we did in the classical framework, in the quantum framework, we want to define the action of the tensor metric on vectors and one forms belonging to the dual space. And we define it, so this is like the geometry, we define it as the expectation value of a symmetrized product between the quantum observables. Skipping the, let's say, some intermediate steps, the key point is that from a geometrical point of view, the distance, the infinitesimal distance on this manifold of density operators, which is given by this expression, so this is like the previous expression that we had in the classical case plus an additional piece, is actually the same one that can be derived from statistical concepts introduced by Brownstein and Caves in their work in 1994, and namely that this line element is equivalent to the distinguishability metric that actually is defined between impure quantum states. So again, following the classical part, we try to do the same thing for the quantum part of Jaynes MaxEnt. But once again, I replace the phenomenon entropy with the quantum relative entropy. And assume that the prior rho 0, let's say it's a maximally mixed state, so it's like a proportional to the entity operator, so that the maximization of this quantity is equivalent to the maximization of the phenomenon entropy, subject to these constraints. And the solution to this maximization problem is the following density operator, let's say. That is parameterized in terms of this parameter lambda, that it works as the Lagrange multiplier. So again, this solution to this maximization problem may be seen as a solution to this differential equation with nonlinear terms. But actually, so from a differential point of view, the MaxEnt estimate can be regarded as a quantum trajectory, this rho lambda, that passes orthogonally through the family of surfaces of constant expectation value, and it goes from rho to rho of lambda equals 0 to to rho of lambda final, going through this family of surfaces. And it stops when orthogonally, and it stops as soon as lambda satisfies the information constraint. Okay, this is just to summarize some of the topics that we have been using. So the key part is that, maybe I was not allowed to do this, but I did it, is that so the MaxEnt entropy, it's, to my understanding, was defined to assign probabilities, and in the classical framework, so assigning probabilities, maximization procedure concerns with the maximization of the Chandra entropy. In the quantum framework, this is replaced by the phenomenon entropy. And of course, there is no concept of a prior and posterior, but so the rationale it's different, but for the mathematical standpoint, let's say, I consider simply maximization of entropy functionals with a uniform prior. So they were the same from a mathematical point of view. Another key point is that I'm not totally confident in using this in the quantum framework. In the classical framework, the same geometric picture may be provided using the quantum relative entropy without assuming the uniform prior. In the quantum framework, I have more doubts about that, since actually I'm not sure that it exists a unique proof that actually shows that this is the quick quantity to maximize in order to update density operators. So in this specific case, the only thing that I can say is that this example gives me some hints about how to get to the MaxEnt estimate in a different way. So this, to me, from this point of view, let's say the geometric interpretation was okay. However, usually it's not always, especially in the quantum framework, it's not so trivial to implement and use these geometric techniques in inference from a computational point of view. Of course, geometry is not going to replace inference. It's simply a tool. And of course, there are some other problems as well. So, okay, this one maybe should be slightly modified, this slide, since what we were talking about yesterday. So the ME method, so the way, so this is mostly a question, for example. If I see the maximum relative entropy method as in the case that we consider constraint functions assuming only two values, that as a method that actually englobes the Bayesian rule and the Jaynes MaxEnt method as special cases, then I was wondering whether or not, since people actually do make comparisons between Bayesian estimates and MaxEnt estimates when they consider the construction of quantum states in the quantum framework. So if they are two different things, maybe there is no meaning to actually compare them. But if they have some overlapping stage, it may be useful to ask whether or not it's possible to devise a criterion that actually englobes both of them, also in the quantum framework. So other problems that actually I never mentioned, since actually I was using one observable, is that something has to be taken care when we consider, let's say, as more than one observables non-commuting, for example, with the prior that I've been using. So there is this emergence of diagonal elements that it was not present into the classical framework. And then another thing that actually arises my doubt, but so I'm opposing this here, is that I think I'm not sure that all the estimation methods have to converge to infinity, because actually, but this is work that I'm trying to understand. So I don't have, I cannot master this. In general, Bayesian quantum inference about determining quantum states depend on the prior as well as the measuring data, even the limit on infinite number of measurements. So I'm not sure that actually all the estimates should converge at the asymptotic limit. So, and then the last part here is simply that is missing, to my knowledge, a formal proof that the quantum relative entropy functional here is one to be chosen to update density operators. And of course, this is from the inference point of view. There are even problems from the geometric point of view, or things that are different going from the classical to the quantum framework. One of them is that, for example, when I have to quantify the notion of distinguishability between quantum states, even pure quantum states, for example, in quantum framework, if I start from the classical Fisher-Rao information metric and I simply divide it in two different equivalent weights from a classical point of view, but then I look at their quantization, I obtain two different metrics that actually are almost equivalent except a constant when I consider the distinguishability of pure states. And then, of course, since I was considering the possibility of studying geodesics on manifolds and Jacobi deviation on the manifolds, I need the line element, then I should integrate the Jacobi equation, but actually I even have problems in finding the line element, so the first step. So, okay, these are some problems, problems in my research. And then some of the works about physics, inference, geometry applied to physical systems appear in some of our works. And this last one, but of course there is not a really clear theoretical framework. Just would like to emphasize this one, was trying to apply information geometric techniques combined with inference methods for the quantification of, from let's say, semi-classical point of view, semi-quantum classical point of view, of the scattering, the entanglement is generated in the scattering between two Gaussian wave packets. So I'm not sure this kind of result, it's not fully justified. I'm not sure that actually relates to the work of the first speaker, but so there are many unclear things, but this is what I was going to say. So thank you for your attention. Most of this work was financially supported by the Connect project, European Union Connect project, and some of the references are listed here. And I would especially emphasize this one, the first one, by Wouters. Thank you.
Okay, thank you very much, Carlo. So we have a couple of minutes for questions.
Can you go back just a few slides? You have a table showing the prior and MaxEnt, ME. Yeah. So you say it's prior, not arbitrary. What do you mean by arbitrary, non-arbitrary?
Oh yes. So there is like I should say known, no prior, because yes. Here. Yeah, I should put no. There's no. In my way of seeing it, no prior, no posterior. Simply from a mathematical standpoint, the maximization procedure using the relative entropy with a uniform prior was equivalent to the maximization procedure with the Shannon entropy. So actually, I should say, yeah, maybe I should use a different notation there.
In the Bayesian framework, as I understand,
yes,
you always have some prior, whether
yes.
I'm sorry. From the Bayesian framework,
yes,
you always have some prior, whether you're conscious or not.
Yes.
So usually, when someone say I have no prior, it's like you have a uniform prior.
Yes.
So I wonder if that's the case for you.
Yes.
Like,
yes. All
is that
everywhere I considered uniform priors.
Uniform priors.
Yes.
Okay. My second quick point is you have the word says Bayesian quantum inference.
Yes.
Does that mean there's a Bayesian
yes,
classical inference? Is that?
Yes. About this I cannot say more, but so for example, so even yesterday during the panel discussion, for example, there were like discussions about MaxEnt, Bayesian. I'm not really capable of actually expressing a meaningful opinion on this, but I do notice that actually there are, like say, people applying quantum this quantum Bayesian rule claim that actually some of the statements provided by people applying the MaxEnt method are misleading. Misleading in the sense that maybe this convergence into the asymptotic limit, it's not really true. So I'm just saying that there are, let's say, problems not only here but even outside. Yes.
Thank you.
Okay, just one quick question. Yeah.
Okay, one. It's really not a question, but a notice regarding this what could be called quantum bias rule. So there are, because you have mentioned this work by Fuchs, and it's actually this what should be considered as quantum bias rule is von Neumann-Rieder's rule. And this was kind of proposed first by Boop in '77 and later developed by Rede and Valente. And basically, it's von Neumann-Rieder's rule is a particular type of, you can generalize it as a particular type conditional expectation. So the question about deriving the quantum bias rule from quantum constraint relative entropy maximization is actually whether is equivalent with a question whether you can characterize particular class of conditional expectations over non-commutative algebras by entropic means. And in this context, it should be noted that in commutative case, there exists a characterization of conditional expectations based on relative entropy made in 2005 by Banerjee, Guo, and Wang. So there is a kind of hope for this type of characterization. This what Fuchs and Caves and others proposed as quantum bias rule is something what is beyond ordinary quantum mechanics in a von Neumann sense, because it's based on positive operator valued measures, and in this sense it cannot be considered as something what fits the framework of quantum mechanics, because then you have semi-spectral measures, you don't have equivalence between self-adjoint operators and observables and so on. So this is something what they propose in their meaning of Bayesianity and quantum information community, but it's not something what is, I would say, mathematically canonical within quantum mechanics.
Okay, thank you. I'll be pleased to talk to you.
Okay, let's thank Carlo again.